Hi everyone, for this lesson I'm going to share with you about electricity. Alright, so in continuation, the electric current, of course you have there the symbol, a big letter I, is the rate of flow of electric charges from one point to another in a circuit. So it means to say that from the main source of energy or the voltage, so the electric current will flow its their charges, okay, one point to another. So from the main source, of course, to the wirings and to the main unit, like for example, a computer. So it is measured in amperes. Okay, you have there the units. Okay, which is of course the amperes and it's A, I guess the symbol. 1 ampere is a rate of flow equal to 1 coulomb of charge per second. Mathematically, electrical current is given by the following formula there, and wherein I, or the big letter I, it stands for the current in amperes, and you have Q is charge in coulomb, and you have the T, which is time in seconds. The standard unit of charge is coulomb. 1 coulomb is the electric charge of 6.25 billion electrons. So if a wire carries 5 amperes and 5 coulomb of charges flow through the wire each second. This means that there are 31.25 billion electrons flowing from one point of a circuit to another. So this is a lot of electrons, okay, right? So it means to say that you get a double, okay, of course, of the flowing electrons when you double the amperes. So how much more if a wire carries 10 amperes? So there's actually twice as many electrons would pass in a cross section each second. Additionally, a sustained current in conducting wire requires a suitable pumping device, meaning charges will flow only when they are pushed or driven. So that's why, for example, a certain source of energy like a battery, okay, it's actually having the voltage. So needed per unit charge to move between 2 points is called voltage. It's expressed in unit of volt. Okay, so you have there these symbols that's actually large or big letter V. Okay, so voltage is what makes a current move. Mathematically, voltage is given by the formula indicated, where V stands for the voltage in volts. Okay, so W, which is the work in joule, Q, charge in coulomb. Okay. Of course, when we say a common automobile battery, as of course shown in the figure 1, okay, later, so we'll provide a voltage of 12 volts to a current its terminals. So when 12 joule of energy are supplied to each coulomb of charge that is made to flow in this circuit. Remember, voltage does not go anywhere. It only drives the charges to move. Figure 2 okay, shows the equivalent electrical symbol of a 12-volt automobile battery. You notice that it has 6 pairs of short and long lines that represent negative and positive terminals respectively. Each pair corresponds to 2 volts. As I mentioned earlier, so this is figure 1. Okay, they have the automobile battery. And so, and of course, the figure 2 is the representation of electrical symbol of a 12 volts battery. So if you notice that there's the indicator there, the positive and the negative charges, and if you count it, okay, the long lines there. So it has 6 of them, okay, and it also has 6 of short lines. Now, when you have to count them. So that's actually 12 in all. Okay, so you have, of course, one of the paired, okay, one long and one short. Okay, so that's actually one, okay, of a pairing, and then second, third until sixth. Okay, so in all you have 12. So we know that batteries and generators are the primary source of voltage in an electric circuit. So please don't forget it. So remember always that the batteries and generators are the primary sources or the main sources of voltage. So there are other, of course, sources of voltage, but this one is for you to remember. So you have the batteries and generators. So how much current exists in a circuit depends not only on the voltage, but also on the electrical resistance of the conductor. So we're going to discuss it with you. I'm going to share with you more about this. Okay, so let me explain a little about the voltage, current, and resistance. So here you have the voltage as the main source of energy or the battery. Now the flow of electrons, okay, going out, okay, from voltage, of course it's driven, okay, going to the wires. Okay, so when all the energy or this electricity, okay, goes out there, it is actually the so-called current or electric current. Now the resistance here means that the things that can, of course, change, okay, the flow of current. So we can control or minimize, okay, the flow of electricity or current flowing through the wires, okay, by first, okay, making a use of the resistors, okay, like that. So we can increase or decrease the flow of electricity. Now, of course, it is another way, okay, that resistance can affect the current is the wires. Okay, so if you use a thicker wire, the flow of the current or electricity is affected too. Okay, so why? Because it is thicker, and the energy that is needed for the flow of energy to go to the bulb to light it up actually becomes lesser. And so if it is thinner, okay, and the voltage is higher, so or just a minimum, so it means that the light bulb, of course, appears to be bright. Okay. Now, on the other hand, okay, another situation is the type of wiring. Okay. So the type of material used. So the more that the material or the wirings are a good conductor of electricity, so it means that it can affect the flow of current. Okay. So anything that affects the flow of current is resistance. Okay. So the current, okay, don't forget, that is the flow of the from one point, okay, from the battery or the main source like that, okay, going to the unit, okay, like the as you can see here, the bulb. Okay, so of course the components, for example, inside of a cell phone. Okay, so if you open it, you can see lots of resistors and others. Of course, the flow of current from the different wirings that they're connected. And of course, the main source of that is the battery of the cell phone. Okay. And with regards to this, okay, they always go together, okay, the voltage, current, and resistance. However, in normal situation, the voltage and current are actually directly proportional to each other. So, of course, if the voltage is higher, okay, the current that will flow through is, of course, higher. So if it is less or lower, so the voltage from the voltage, the current, electric current, of course, is lower. Okay, though the resistance, the one that affects the current flow, okay, of the electricity. Okay, so that's why in every appliances or every appliances that we have, okay, we can notice that the purpose of those resistors, okay, to control the flow of electricity to avoid the explosion, okay, like that, okay, or malfunction of the appliance. So I think that's very important for you to learn about this. Okay, so I'm going to give you more, okay, or specific situations regarding this later on. All right, so in continuation, electrical resistance, I guess I've already gave you some examples a while ago, is the opposition to the flow of current by the conducting wire. So the electrical resistance of the wire depends on its thickness, length, and conductivity, as I've already explained a while ago. So thick wires have less resistance than thin wires because thick wires have greater cross-sectional area for the electron to flow than thin wires. So moreover, longer wires have more resistance than shorter wires because longer wires have longer path for the current to flow. Okay, so that's very a clear explanation. Okay, so copper wires have less resistance than steel wires for the same size because copper has higher conductivity than steel. So conductivity is the property of matter that allows current to flow. The higher the conductivity of material, the more current can freely flow. So electrical resistance also depends on temperature. Okay, so at higher temperature, atoms are violently vibrating than that, or that can result to greater collision, creating more resistance against the flow of current. So electrical resistance is measured in ohms. Okay, so named after George Simon Ohm. So as you can see the figure 3, okay, it's a resistor, this one that I'm saying a while ago, that can also affect the flow of current, or it can be one of the resistance, okay, in the flow of electricity. So an electronic device that is designed to resist the flow of current is known as resistor. Okay, so as you can see on the picture or the drawing. So its equivalent electrical symbol in figure 4. I guess you can see that there. Okay, so that's the symbol of a resistor. Okay. So a resistor can also be a light bulb, okay, as mentioned here, because as you can see also on the figure 5, okay, and corresponds to the figure 6, is the electrical symbol of a light bulb. Alright, so the representation here of figure 7, the relationship among voltage, current, and resistance is summarized by Ohm's law. Okay, Ohm, okay, discovered that at constant resistance, okay, so it means to say that the resistance is not changed, okay, in a particular unit. Okay, the unit that I'm referring to is the appliance, for example. So the current in a circuit is directly proportional to the voltage established across the circuit, as graphically represented here. So as I've mentioned earlier, okay, that of course it is directly proportional. So the voltage, the of course electrical energy that is driven out, okay, as a current, is actually equal to that, or directly proportional. If it is higher, so of course that's the release or amount of voltage or electricity, or the electrons that's going to pass through the wire. Now the resistance here, as mentioned, okay, is actually at constant, so it's not being changed into higher or lower than that. Okay, so it depends on if you, of course, open a certain or know a certain appliance, so there are resistors there, okay, in the other of course established, okay, electrical wirings. All right, so this is the first explanation for this. All right, so for these figures, okay, for given values of resistance, current, and voltage, okay, as you can see on figure 8, okay, so this is on figure 8, it's the initial values of voltage, current, and resistance. So it means to say that it's at constant. Now, if you look at figure 9, okay, so we increased or double the voltage, okay, at constant resistance. So what's going to happen with the flow of electricity or the current? Okay, it's actually doubled also. So because as mentioned, okay, it is directly proportional. Now, with regards to the uh, current, okay, going on with the figure 10, okay, that is inverse relationship, okay, of resistance and current at constant voltage. So the voltage is constant, so we did not change it, okay, though it lowers down, including the or decreases, including the electric current flowing, okay, towards the unit or a particular appliance, because of course the resistance here were increased. Okay, so remember that the resistance are, for example, the resistors and the type of wiring. Okay, and of course the another thing is the thickness or the size of the wirings or those included in the circuit. Okay, so that's the explanation, okay, for these figures. Alright, so for computation in a simple circuit, voltage is directly proportional to the current. Its proportionality constant is R, okay, for the resistance. And so you have to use the voltage formula is equal to the current. And so, of course, multiplied by the resistance. Okay, so you have there the meaning of those symbols. Now, example number 1, okay, find the resistance of a kilo ohm of a single motor horn if it has a voltage of 6 volts and current of 2 milliamperes. So given here, okay, you have the voltage, okay, which is actually 6 volts, and the current is 2. Then we have to convert it into the given ampere, okay, as of course needed. The MA, of course, it stands for milliampere. So for every 1 ampere, we have 1000, okay, milliampere. So that means, let's say that we have to convert it, okay, and you will get 0.002A. Now it is required to get the resistance, and the solution for this, okay, follow the Ohm's law, first formula. Then since the resistance is required, so you have to divide, okay, the voltage over the current. Okay, so you have there 6 divided by 0.002, and then you get here the equivalent of 3 kilo ohms. Okay, that's the answer. Okay. Alright, so for example number 2, computation. So if a circuit has a resistance of 44 ohms and a current of 5 ampere, what is the voltage? So given, okay, so you have there 44 ohms and the current, okay, so you have 5 ampere, and the voltage, okay, you have to know, okay, the equivalent of this. So just multiply 44 times 5, and then you'll get the voltage, which is equal to 220 volts. So that's the solution and answer for this. Alright, so for the example number 3, computation. What will happen to the current if the resistance is tripled? State the relationship of current and resistance based on your answer. So you have here the voltage formula, which is equal to the current multiplied by resistance R. So originally, as the of course current is the one of course needed from the problem, so that's why we have to represent that is equal to voltage divided by resistance. So if R is tripled, then so as indicated, okay, you have to of course shown here, okay, that 1 over 3, okay, as represented for the voltage 1, okay, over, and then 3 is the equivalent of resistance, or 1 over 3, or 1/3. Therefore the resistance is tripled, the current is reduced by 1/3. The result shows that when resistance is increased at constant voltage, the current is reduced. So this is the explanation for this example number 3. Okay, so in summary, okay, the current is directly proportional to the voltage and inversely proportional to the resistance. So doubling or tripling the resistance will cause the current to be 1/2 or 1/3 the original value. Thank you very much. That's everything for this lesson about basic electricity.